So we're going to focus on division, but doing division with polynomials. So before we dive into what it looks like with a polynomial, the process is technically the same as when you do it with numbers, but of course it looks a little more different and complicated when using polynomials. So let's just review how we do long division with numerical values. So if I was taking 3051 and dividing it by 4, my first goal would be to try to make the number as close as possible and see if there's any leftovers. And we do that by actually looking at the higher place values and trying to match that first and then working our way towards the right. And we're going to do that same thing with our polynomials. So since 4 can't go into 3, we look at 30, and 4 goes into 37 times. And 7 times 4 gives us 28. So we decide what we can get that matches or comes closest to matching that first amount. We write what that leaves us with. And then we subtract the difference. I'm actually going to do that in a different color just to emphasize that we are subtracting. 30 minus 28 leaves us with 2. And we drop down the next value of 5. Now we're going to ask ourselves 4 times what makes 25. So the closest we can get is 6. And we multiply those together. 6 times 4 gives us 24. And again, what are we doing with those values? We are subtracting them. 25 minus 24 leaves us with 1. And we drop down the other one. How many times does 4 go into 11? Twice. 4 times 2 gives us 8. And again, we are subtracting those values for a final remainder of 3, a value that's smaller than 4, and that's how we know that that's our remainder. So just some vocab in case it gets used throughout here. This is your dividend. This is your divisor. This is your remainder. And then the answer to the division problem is your quotient. And in this case, our quotient would be 762 with a remainder of 3. Now, way back in the day, you'd write like the little r with the 3. And then we got a little more specific mathematically, and we write that that's 3 out of 4 left over, that we can write that as that fractional value. So now we're going to try and use this same process with a polynomial. So you'll see here I have one polynomial divided by another. So the first thing I want you to notice is that the polynomials are written in standard form. And standard form means we have our terms of highest degree down to our terms of lowest degree. Now, if you want your terms to line up correctly, when you have something missing, like notice how this goes from the 4th degree to the 2nd degree and there's no 3rd degree term, you actually want to think about this as having 0x to the thirds. Now, that's kind of meaningless. That's why it wasn't written here to begin with. But what it's going to help us with our division problem is help things with like terms line up. Just like you had a 0 up here in your division problem, if you didn't write that, your 3 could have possibly gotten confused as belonging in the hundreds spot rather than the thousands spot. And we don't want to accidentally combine together any like terms that aren't actually like. So we want this 0 placeholder anytime we're missing a power that's somewhere from our highest degree term down to our lowest degree term or our constant. So we always want the highest power down to the constant with no missing terms. So I'm going to now set up this division problem. So 4x to the 4th plus 0x cubed minus 5x squared plus 2x plus 4. Now that's being divided by 2x minus 1. Now, it's a little harder for our heads to wrap around exactly what we're going to multiply 2x minus 1 by to get these. But again, we're going to come back to the same idea we did here. We didn't really think about how many times 4 went into the entire 3051. Instead, we focused on the places at the beginning of the number. So we're going to focus on this first term. Now, in order for this division to work like you saw before, notice that we moved over place value as we did the division process. Like we started in the thousands place, but then we were working in the hundreds place, then the tens place, and then the ones place. That kind of automatically happens with numbers because you're reducing the number every time. With polynomials, you have to be a little more specific. It's only going to go in that direction if you completely get rid of x to the fourth. If you don't completely get rid of your x to the fourth term, you're going to continue to have x to the fourth, and you're not going to make any progress in narrowing down what's left. So the one thing that's a little different here is that we don't just try to get close, we need to get exact. We need to make exactly this first term. So you're picking something that's going to multiply 2x minus 1. It's going to make obviously something with two terms. I don't care as much about the second term, but the first term must be exactly the same as 4x to the fourth. So really what I'm asking myself when I'm deciding what goes here is, what am I going to multiply times 2x? This is kind of what I'm focusing on, just the first terms. 2x multiplied by what is going to give me exactly that first term, and then I'll deal with the other spaces or places in the polynomial as we move forward in the process. So I know that 2 times 2 would make 4, so I want a 2. And the 2 already has an x, but I want to create x to the fourth power, so I'm looking for x cubed. So I'm going to choose 2x cubed. Now after my choice, that value, just like with your numerical division, once you choose a number up here as part of your quotient, it multiplies this divisor. So I need to multiply 2x cubed times this entire quantity, which means it's going to distribute to each of these terms, and it's going to give me two terms. And the first one hopefully is 4x to the fourth, because that's how I planned it. So 2x cubed times 2x is 4x to the fourth, just like we wanted. And 2x cubed times negative 1 is negative 2x cubed. Now remember that you are subtracting these. And with polynomials, because these have two pieces, you have to remember you're subtracting this whole thing. That means that negative applies here and here. When we distribute that negative, it means the 4 will become negative and the 2 will become positive. And this is what we want to happen. 4x to the fourth and negative 4x to the fourth gone. And then we combine 0x cubed with 2x cubed to get a positive 2x cubed, and we drop down the next term. Now we start the process again. What am I going to multiply times this polynomial to get as close to this as possible, but I'm focusing on those first terms, the highest degree term. What do I want to multiply by 2x to make 2x cubed? And so for me, that's going to be x squared. So I'm going to choose that the next thing I'd like to use is x squared. And then remember that I need to multiply this entire divisor by x squared. So x squared is going to distribute to 2x and to negative 1. So x squared times 2x is 2x cubed, and x squared times negative 1 is negative x squared. And remember what we're doing with this quantity. We are subtracting this entire quantity. That means that minus gets distributed. So if we change this to addition, that's fine as long as we distributed the negative. So it's a negative 2x cubed and a positive x squared. This causes the first term to cancel out, which is what I'm aiming for every time, to work with lower degree terms and be making progress in this division problem. And that leaves me with negative 4x squared here, and I drop down the next term of 2x. So I'm going to continue this process. I want to fill in the next spot. In the next spot, I would be asking myself, what do I want to multiply by 2x minus 1 to get negative 4x squared plus 2x? Again, focusing on the first terms matching. What times 2x will make negative 4x squared? So I would choose negative 2x. Negative 2x times 2x makes negative 4x squared. Negative 2x times negative 1 makes positive 2x. And remember that we are subtracting these values. So if this negative distributes to each of the terms, I get a positive 4x and a negative 2x, a positive 4x squared and a negative 2x. So these terms cancel, but so do these. So I'm going to write this as this. I have 0x, just because I really want to thoroughly check what's happening in my problem, plus 4. So what would happen next is I would multiply by a 0 technically, and I know that some of you are going to be able to see patterns here where you don't feel like you have to do this, but we want to be really thorough. 0 multiplied by each of these would make 0x, and 0. And even if we change those signs, that's going to leave us with 4. And this is our stopping point. When you get to 4, notice that it doesn't have any powers of x. The degree of this, 4, is a constant. It would be of degree 0. Our divisor is of degree 1. We can no longer do division because we've reached a point where our leftovers are a lower degree than what we were dividing by. Okay? So this problem asks for the quotient and the remainder. So if they just wanted to know the remainder, our remainder is 4. So 2x minus 1 does not divide this polynomial evenly, as you guys like to say. Okay, it does have a remainder of 4. So the quotient, the answer to the division problem, is that 2x minus 1 would make that original polynomial 4x to the 4th minus 5x squared plus 2x plus 4 if it was multiplied by 2x cubed plus x squared minus 2x. You don't have to write the plus 0. We do need to include the remainder. Remember that we write our remainder like a fraction, and since it's a different degree of x, we separate it with an addition sign just like all the other terms. So 4 is left out of what we were dividing by, which is 2x minus 1. So this would be our quotient, and we can see that remainder of 4. So long division, really similar to how you've done it before. But division has this pattern to it. And so like we've seen with a lot of things, we can generalize that pattern. And when that happens in mathematics, oftentimes they come up with a new process or procedure, kind of like you guys saw with completing the square and quadratic formula. Completing the square was the same rigorous process that you went through each time. So we saw that, well, a mathematician came up with the quadratic formula, which is really just completing the square, but more generalized in the process. So since division is kind of like that, it is the same process over and over again that we're doing every time. They came up with a simpler way to represent it if you know what's happening. If you don't know what's happening, it could get a little chaotic. So they do what we call synthetic division. You don't see all the pieces here. You're just kind of going through the motion with the numbers, and then you have to interpret the answer. So first you have two polynomials divided by each other. Okay? And so here's polynomial number 1, my dividend. And here's polynomial number 2, the one that's doing the dividing, my divisor. And here's how you set up synthetic division. First, you set up all the numbers, the coefficients from this polynomial in a line right here. So 2, -5, -14, 47, -30. Why do we do that? Well, because really what we were doing each time up here is we were trying to match that lead coefficient. And then the next time what you were seeing is a combination of those things with something else totally dependent on the next number in the sequence. So some result that you got from your division was being added or subtracted with something else. So we know that these numbers are key in adding and subtracting. Now, the 0 placeholder is extra important here because you can't even see the powers of x's. Like this is x to the 4th, but we don't see that next to it. So we are assuming that you have highest power all the way down to constant here. So if you were missing anything, you would definitely need a 0 placeholder. Then over here in this little kind of like box area is a number, and it is basically, they wrote it like this, the k from the x minus k. Another way to say it is that it's the 0 of the divisor. So if you took what you're dividing by and set it equal to 0, that x value that you would get is what you're using here in this spot. Now this process only works for divisors like this. They have to be linear. That means of degree 1. And x has to have a lead coefficient of 1. Because remember, these processes, when we're kind of taking out all the notation, it's great in one sense, but in another sense, it's just like completing the square. It only works, this pattern, from a very specific perspective. So this division pattern only works if we know that 1 is in front of x right here that you're dividing by. Otherwise, if the numbers changed every time, like in this one how we had a 2, it would change the different numbers that come out here, and I couldn't generalize the process. So we can only do it when there's a 1. And then here's what we do. The first thing we do is we drop down the first coefficient, because if it was a 1 that you had right here, compare it to long division. If you were trying to take x minus 2 and divide it into this long polynomial, the first thing you would choose, if this is a 1, would be exactly the same number that's here in your polynomial, because that number times 1 would make itself. So this is why this only works with 1 and why we have to generalize it. So we drop down 2. Then what do? We multiply. So the 2 in here times the 2 right here. So every time we get a number down here, it's being multiplied by that 0. So 2 times 2 makes 4. And then when you get numbers in the column, you add them together. Okay? Because they've already switched the sign by using the 0 here. So you're not subtracting, you're adding. -5 plus 4 is -1. Now that we have a new number down here, it multiplies the number in the box 2. 2 times -1 makes -2. And then we add up the column. So -14 plus -2 is -16. Now -16 multiplies -2. That gives us -32. -32 is added with 47 to give us 15. 15 times 2 gives us 30. -30 plus +30 is 0. So there's the process, but like, what the heck is this? Well, this is all of your work in the second row. This is supposed to be your quotient. This is your answer. What happened when you divided that in, but it doesn't look like an answer. So you do have to do a little bit of process. Think about what you were doing. You were taking something that was of the 4th degree and dividing it by something of the 1st degree. So I'm going to think about that in the simplest terms. If something to the 4th degree is divided by something to the 1st degree, our exponent rules say that we subtract those exponents and we get something to the 3rd degree. So my answer should be a polynomial to the 3rd degree. It should actually always be 1 less, right? Because I'm always only dividing by a linear factor. So that means it's of degree 1, so it's always lowering it 1 degree. So if the 2 used to be x to the 4th, now this term is supposed to be x to the 3rd. And then remember how things get written in standard form. If we've accounted for every spot, they just go down a degree with each term. So that's a cubic term, a quadratic term, a linear term, a constant term, and this last spot would be our remainder. So in this problem, we have no remainder. That means it divides evenly or is a factor of this number. So what is the answer when I actually do this division problem? This giant quartic divided by x minus 2 leaves us with 2x cubed minus x squared minus 16x plus 15 with no remainder. And I'm getting that answer from that last line down there. So we're going to just go through a couple of examples. So first example is going to be set up the same way. The factor is x minus 3, so I would use 3 in the box. The coefficients go from a cubic down to a constant with lead coefficients of 6, -19, 1, and 6. So I drop down my first term, I multiply, and I add up the column. I then multiply again and add up the column. I then multiply again and I add up the column. Now these aren't all going to work out to have a remainder of 0. So I had a cubic and I divided it by a linear term, so I now should be left with a quadratic. So these are kind of how my terms will work out, meaning that the answer to this division problem is 6x squared minus x minus 2. All right, so part B is a little more complicated because I told you guys you needed a lead coefficient of 1 and it doesn't have a lead coefficient of 1. So if you really like synthetic division and you still want to do that instead of long division, there is a way around it. We basically want to work like we do with common factors. Like, you know, if you have a, let's say 4 over 8, no, let's say 6 over 8. You guys can cancel out the 2 because 6 is like 2 times 3 and 8 is like 2 times 4. So we take out that common factor of 2 and we say, well, 6 over 8 is really the same thing as 3 over 4. So like if you did in a calculator 6 divided by 8, you would get the same decimal as if you did 3 divided by 4. So what we want to do is turn this division problem into something different. So right now, if we viewed this division problem in this like fraction perspective to understand how to take out a common factor, it looks like this. If we're not allowed to have a coefficient of 2, we would have to rewrite this with the 2 factored out. And yes, that's going to leave a 1/2 in there. And then I'm forced to factor out a 2 in the numerator because I'm trying to get a factor that cancels out. So whether the numerator has stuff that's divisible by 2 or not, that's how I'm writing it. So this is what I get so that these 2's can cancel out. So that this 4x to the 4th polynomial divided by 2x minus 1 is really the same as this 2x to the 4th polynomial divided by x minus 1/2. And now I can use synthetic division because it fits the pattern now. It's a linear term with a lead coefficient of 1. Now, the fact that I'm dividing by x minus 1/2 means that 1/2 would be the number that's in that box in our synthetic division process, and that these are now the coefficients that we want to use to set up the process. So 2 is the coefficient of x to the 4th. I need a 0 placeholder because I don't have an x cubed. I have negative 5 over 2x squared, 1x, and 2. So I drop down 2. 1/2 times 2 is 1. I add that column, I multiply, I add that column, and in this case I'm going to rewrite that fraction since it can be rewritten as a whole number. I then multiply, I add the column. Don't stop because you get a 0, you need to finish the process, so I multiply and I add the column. So in this division problem, here's the answer that I get. And again, because I started with a quartic divided by a linear term, my answer should be a cubic. So I'm kind of looking at what those terms should be. So my answer here is 2x cubed plus 1x squared minus 2x. I don't need to write the constant because it was 0, but I do have a remainder of 2 over x minus 1/2. And then this is kind of a bummer, but it just comes with this procedure because we had to divide everything by 2, even if it didn't nicely work. We really don't generally want to leave fractions within fractions in our final answers for things. So I would want to multiply this by 2 to cancel out the fraction of 1/2 and no longer have a fraction there. That's okay because this is a fraction as long as I also multiply the numerator by 2. So the way I would write my very final answer for this is 2x cubed plus x squared minus 2x plus 4 over 2x minus 1. And that would be my quotient.